Let's analyze the function f of x equals to 7x minus 4 ln x. And x have to be positive, it's inside of the log, so that makes sense that this is part of the domain. Domain is 0 plus infinity, not including 0. By analyzing the function means we're going to be answering lots of questions about where this function is increasing, decreasing, local, global, min, max, concavity, inflection points, and at the end we're going to sketch the graph. Solution. The first question we are asked as always, is about the critical points, because basically it's part of the increasing, decreasing questions. So step 1, let's go to A, critical points. To find critical points, we know how to start. F prime of x is 7 minus 4 over x. Do you know how I got 4 over x? Derivative of log is 1 over x, and then multiplied by -4. So I highly recommend to create a common denominator. I always say to do that. It's just easier to work with one fraction rather than fraction and little piece outside of it, or two fractions. 7x minus 4. What do we do now to find critical points? Correct, we need to find where this derivative is 0. That comes from the numerator being 0. But don't forget about the bad points, and I mean bad, like so. They call singular points. That means where derivative does not exist or not defined. So those points are coming from the denominator of this fraction. Well, x cannot be 0. It's given over here in a domain. So this point is not a critical point. In fact, it's probably some kind of asymptote or something like that. Well, let's only solve the numerator. 7x minus 4 equals to 0. 7x equals to 4. X equals to 4 over 7. Before claiming that this is a critical point, I need to check that it is in a domain. Remember, critical points are only points that are in the domain. Domain of what? Domain of the original function. And it is, because the domain says x have to be positive. So it is indeed a critical point. Now, we can include that in our first answer. B and C are asking us about increasing, decreasing intervals. To do that, so B and C go together. I will sketch the sign line. So the first derivative test. You can do the second derivative test if you want. But that's mostly for the minimum and maximum. So the first derivative test, I'll draw the sign line where x is the input. The sign line is for the derivative, not the original function. I'll put the critical points on the sign line. I also indicate that it have to be positive. And now I will choose test points on each of the interval and substitute them into the derivative. Remember, not the original function. So 4 over 7 is not half. So I can use 0.5 or 0.1. And then I can use literally anything huge, even a million if I want. But 10 is fine too. Actually, 7 over 7 is bigger than 4 over 7, so even 1 helps. Those are my test points. I only need to know the sign of the first derivative at those test points. The first derivative at 0.1 will be, and now I'm looking at 7, 0.1 minus 4 divided by 0.1. Well, when 7 is multiplied by 0.1, it becomes 0.7, and 0.7 is definitely smaller than 0. So it's smaller than 4. So it is negative. Thus, the whole result is negative. Thus, I can put the negative sign over here. See, I don't have to actually know the number. It's kind of wasting my time, especially on the test. I would like to be fast, so it's nice to be fast. 7 times 1 minus 4 divided by 1. I only need to know that 7 times 1 is bigger than 4. So I don't care what the answer is, even though it's kind of easy in this case. I just care that it is positive. The first derivative is positive after 4 over 7. Thus, the original function, which is c, why did I call it c? Oh, I don't know why I call it C. It's f. F prime, and the original function is f. Probably I want to write critical point, that's why. F prime, and then the original function is f. The original function is decreasing up until 4/7, and then is increasing after that forever. And also it's not decreasing from minus infinity, it's decreasing from x is 0, not including 0. So let's answer the questions. The first question asked about increasing interval. So B says, where does the original function increasing? Well, the derivative is positive on 4/7 to infinity, not including 4/7. So that is where original function f of x is increasing on 4/7, infinity. Don't ask me why the red color is so fat. Let me decrease the fatness. C is asking about a decreasing interval. And to be consistent, I'll write down for you that derivative was negative on 0 to 4/7. Thus, so I'll put then like so. This means then. Then original function is decreasing on that interval on 0, 4/7. Does that make sense? Why do we not include 4/7 in all of those answers? Because what is the sign of the derivative at 4/7? It's 0. That's how we found it originally. So it's not negative and it's not positive. The original function is neither increasing and not decreasing at that point. So we don't include it into the answer. Now, D and E are asking about local min and max. D says, can you find, please, local maximum? Local maximum. And then E is asking about local minimum. And all of this is coming from the same sign line. That's why I like it so much. So I can see that since the original function was decreasing and then increasing, then at 4/7 we can observe local minimum. And there's no local maximum. Moreover, this local minimum is also a global minimum. Do you know why? Because the function doesn't have more critical points, so it never has another point to change the direction and dive deeper to another minimum. Thus, it will always gonna go up after 4.7. That means that this is the lowest height this function can reach. The lowest height, that makes sense? The lowest output. So what do we answer about the maximum? None. What do we answer about the minimum? X equals to 4/7. Well, that's actually not correct. We need to give a point, you know? So we need to say what is the input and the output. The point will be point, unless they don't ask you about it. That's actually a good point. If they only ask about the location, the input for the local min or max, then you only input x. But it is professional to input both 4/7, comma, and now you go back to the very original function and write down that the answer for that will be 7 multiplied by 4/7, which simplifies nicely, minus 4 natural log of 4/7. And that is some kind of value. And of course, you could simplify that. So that is your input and the output. That is minimum, local, and global, even though they did not probably ask us about that, about the global part. Minimum, local, and global point. Good. Continue this quest on the analyzing of the function. So F is asking about concavity. Let me read for you from the screen. Use the internal notation to indicate where f is concave up and g is concave down. Oh, actually it doesn't ask about concave down, because guess what? It's not concave down anywhere. So let me write down concave up and down. And that's usually the next question. After the first derivative, we're going to second derivative. You remember, right? Concavity is about second derivative. So I need to find f prime prime of x. So let's go back to f. Where is the f function? Here you go. And I need to find the first derivative, which we already did. And now I need to differentiate again. Choose your enemy. Which one do you want to differentiate? 7 minus 4 over x, or the using quotient rule 7x minus 4 over x. So in this case, I actually like the original version, 7 minus 4 over x. I'll differentiate that. Just looks nicer. 7 minus 4 over x. So working with the fraction is easier until you start differentiating. Then I would differentiate the original version. 7 gives me 0. Minus minus gives me plus, and it's going to be 4 over x squared, following the same logic we had before, that 1 over x can be written as x to the minus 1. So you see how nice? That's a very nice second derivative. Put this in the box. So again, we're doing the same process. Where is it 0 and where it doesn't exist? There's no, well, x is not 0, so there's no bad points here. We only need to figure out where it is 0, but that comes from the numerator. 4 cannot be 0. Thus, 4 over x squared cannot be 0. Thus, we can say that there's no solutions. Why did I switch to red color? No solutions. Actually, let me just keep it like so, short. No solutions for that. Thus, what does it even mean? There are no inflection point here, because remember, these points usually give us the inflection point. Well, I don't understand what to answer about concavity. When is concave up and when is it concave down? I will draw a sine line with x as an input, but it's going to be for the second derivative. And on this sine line, I usually put the solutions of the second derivative that comes from the second derivative being 0 or d and e. Now, there's no solutions, so I only indicated it should be positive. The x cannot be 0 or negative. And now I need to figure out if the original function is concave up or concave down. To do that, I perform a second derivative test. Choose any test point, for example, 1 or 10 or a million. This time it doesn't matter. It's a test point. And substitute it into the second derivative. The second derivative at 1. I just need to know the sign. With 4 over 1 squared. It is positive. Wait, didn't we just said that it cannot be 0, but it also because of the squared in the denominator and positive number in the numerator? Actually, it's always positive. Because the second derivative is always positive. Second derivative positive for all x in the domain, and it means positive, right? It means all over here, everywhere. The original function, f of x, is concave. Do you remember up or down? Did you memorize? I like to teach it with funny emojis. So if the second derivative is positive, the original function is smiling, and the tongue is the local minimum. If the second derivative is negative, then the original function is grumpy, and the nose is the local maximum. So concave up for the first case and concave down for the second case. Concave up for all x in the domain, and concave down nowhere. So we can just skip that. The question G asks about inflection points. Inflection points, or points of inflections, they change the concavity, but the function doesn't change the concavity, and that is why there were no solutions for the second derivative to be 0. There is no inflection points or points of inflection. Finally, it's time to draw. What do we know about the function? From this knowledge, we can sketch the graph. It doesn't have to be precise. We just want you to be comfortable with using all this given information and knowing some kind of approximate visualization of the function. So we're trying to draw the function 7x minus 4 ln x. We learned that it is always concave up, so it will be a kind of like a cup or a smiley looking shape. It doesn't go to the negative side of 0 or even at 0. So it's only here. X have to be positive. Then we also know that there's an important point which was called what? 4/7. Let me put it here. So the function was decreasing before 4/7, reached its local global minimum, and then increasing forever. That's how you can see it. And you know, it's kind of like a dumb graph, but at least we know it probably has a vertical asymptote, which you could try to figure out, this and that. I have a professional graph for you. Ta-da! I prepared it for you. A very sneaky move that I actually knew ahead of time how the graph looked. Here you go. 4/7. The original function was decreasing before that, then it was increasing after that. The original function is always concave up. And this point over here is local, global, minimum. Isn't cool? So here is the result of the analyzing the function that was called 7x minus 4 ln x. Thank you for paying attention for so long, and good luck with all of your other homework problems.